The difference between conventional, inorganic laser diodes and organic laser diodes is that the ease of deposition and wavelength tunability of organics may be worth their drop in mobility and thermal conductivity. While electrically driven lasers are generally based on PN junctions, the difference I want to highlight is that organics operate in a fundamentally different way. Conventional laser diodes replenish the supply of electrons and holes needed for emission via a diffusion current and have heavily doped active areas. For organics, the high doping levels are still required for ohmic contacts, but any dopants in the active layer would quench emission. Without dopants, the band diagram looks like an insulator. Organic laser diodes are not driven by a diffusion current, but by a drift current, and the high carrier densities needed for lasing only exist under bias conditions. A higher bias results in more carriers, and more carriers reduces the resistance, hence space charge limited current. Similar to the unipolar case, that's more common. Current is related to the square of the voltage and is described by the Mott-Gurney law. But in this bipolar case, the effective mobility comes both from electrons and holes and is enhanced by the recombination. The Langevin recombination, common to organics, results in a special case that allows this to be treated analytically. So the value of the effective mobility is about 3 times that of the average mobility, although we will mainly be focused on the ideal case where the electron and hole mobilities are equal. Using parameters similar to that of the first demonstrated organic laser diode, the analytic treatment predicts this square law dependence, while full drift diffusion simulations show the same behavior after the space charge set up by the bias exceeds the background levels. This mobility is higher than is typical for an organic, but under these high field and carrier concentrations, a higher mobility results in these disordered systems. This relationship is the result of simulating with a Gaussian disorder mobility model. And putting the average mobility back into the analytic treatment, the underlying behavior is still captured. But the accuracy of these predictions requires using a mobility model congruent with lasing conditions. Looking at the important parameters for biasing and thermal management, the current threshold depends on the length of the device and the rate of electrons recombining with holes for lasing, which is really just a statement of particle conservation and balanced charge injection. The voltage follows from the Mott-Gurney law. The next step is to work out the required recombination rate, which means we have to work out how many singlets are needed. Focusing on the singlets in the active area, the gain depends on a few parameters. The density of singlet states for 1, or more importantly, the number above the transparency density. Second, each of the singlets have a stimulated emission cross-section to interact with the lasing mode, and not all of the mode necessarily overlaps with the active area. Some of the mode will interact with structures that will add to loss, but even if we could remove all of these losses, the nature of populating singlet states electronically will add additional loss. If we focus on a molecule, a singlet is composed of 2 electrons with spins out of phase, one in the highest occupied orbital and one in the lowest orbital that would normally be unoccupied. As the lasing mode passes, the singlet can recombine and add to this mode. But we also have triplets and holes and electrons, which can't contribute, but will have allowed transitions that can subtract from the mode. And if this absorption is possible, then singlets can be annihilated by resonantly transferring their energy. With the gain equal to 0 at threshold, singlet density needed is the transparency density with an additional factor for absorption. Normalizing this parasitic absorption to the absorption that was overcome to reach transparency allows us to gauge its impact. In order to maintain a singlet population, electrons and holes will need to recombine and replenish the natural decay of singlets, with both the absorption factor and an additional factor for annihilation. Understanding these losses will require a better understanding of the positional dependence of the carrier densities. The position can be related to the fraction of the current supplied by electrons. This Jn term also nicely parameterizes the carrier densities. The hole density consists of 2 main terms, and the position-dependent term is independent of the bias term. So with equal mobilities, the electrons necessarily mirror the holes. But in our case, the product of the 2 cancels out the position dependence, and the recombination rate is uniform everywhere. This results in a uniform density of singlets and triplets. While these expressions break down near the contacts, there's not an infinite amount of carriers at the contact. Before the value explodes, the carrier concentrations at the contacts are roughly a factor of 10 higher than at the midpoint. And in many drift diffusion simulations of different contact dopings and different mobilities, the charge balance goes to unity after this factor of 10 observation is reached. Now with the position dependence, we can re-examine the absorption and quenching terms. While the uniform case of triplets is easiest to understand, this applies in the same way to our carriers. If the absorption cross-section is sufficient, it necessarily lowers the gain. But in this material, a higher annihilation rate by triplets would also be likely. Now to some extent we can compensate by recombining more and boosting our singlet density. But at the same time we will generate more triplets, increasing the absorption and annihilating more singlets. It's easy to see how this could get out of hand. So going back to our threshold recombination rate, if we use the profiles we found earlier, this fills in the details of this expression, and a few things are worth highlighting. One, this is a quintic equation and you can solve it. Second, it's easier to understand and work with the threshold density that includes the cold cavity absorption, which is the threshold you would measure optically. In this form, the absorption and annihilation terms are written in nearly the same way, with a triplet part and a polaron part, which we are considering as either electrons or holes, hopefully not both. The polaron term approximates the positional dependence as if it were uniform, using an average for the absorption and an exact solution when the polarons are sufficient to have the singlet density. But the more important part is that they scale with the square root of the recombination rate. Moving to the triplet terms, these scale with a more aggressive linear dependence. Note how important the rise time of the electrical pulse is to the impact of triplets. You're gonna need to pulse fast. Some combinations of these parameters will not have physically meaningful solutions. Looking at the boundary of finite real-valued solutions, for triplets alone the bound forms a parabola. Again, note the rise time in the right-hand side of the inequality. This term is simply the ratio of singlets to triplets, and the intercept of the y-axis is where the ratio of absorption to emission cross-sections equal the ratio of singlets to triplets. The x-axis is a bit harder to see, but in this form it occurs where the triplet density at the minimum possible threshold will annihilate singlets at the same rate that singlets decay naturally. If these were taken independently, the full parameter space of absorption and annihilation by triplets would be this. But the combination of the two severely restricts this space. For polarons, the boundary takes a slightly different form, and only exists if absorption and annihilation are taken together. Say this is due to holes. The rate at which a hole can annihilate a nearby singlet cannot exceed the rate it can recombine with a nearby electron to form a singlet when scaled by the absorption and emission cross-sections. Putting some numbers to these using the same parameters as before, and with a stimulated emission cross-section of 2 by 10 to the negative 16 square centimeters. For triplets, these two lines are the difference between doubling your threshold current and preventing lasing altogether, even for a 10 nanosecond rise time. It's probably not surprising to some to see ALQ DCM fall on the wrong side of this line. For triplets, they either have an effect or they don't have one at all, and there's not much of a middle ground. Shifting over to polarons, the band between doubling your threshold and outright forbidding it is less aggressive. But if you consider 4, 8, or 16 times higher thresholds, it really doesn't make polarons that much easier to deal with. Drift diffusion simulations validate the approximations used earlier, particularly when polarons have any noticeable effect on threshold. Understanding that lasing from organic semiconductors is driven by bipolar space charge limited current gives you the basic relationships needed for designing devices and the speeds they need to operate at, but it can also tell you if a particular organic material is even capable of making a laser diode. I would also like you to think that the first demonstration of an organic laser diode was not just an achievement in making an organic laze electrically, but it demonstrated lasing operating in a fundamentally different way to a conventional laser diode. I want to specially note the papers for the first demonstration of an organic laser diode, as well as the solution to bipolar space charge limited current. We've written a manuscript on this, but it's in the review process at the moment. A preprint can be found on arXiv here. Thank you for watching.